Metabolic syndrome is a complex and multifaceted condition that encompasses a cluster of metabolic abnormalities, including insulin resistance, dyslipidemia, central obesity, and hypertension. It represents a major public health concern due to its association with an increased risk of cardiovascular disease and type 2 diabetes. In order to fully understand the pathophysiology of metabolic syndrome, it is important to explore the intricate mechanisms underlying each component of this syndrome. Insulin resistance is a key factor in metabolic syndrome, leading to dysregulated glucose metabolism. Target tissues fail to respond efficiently to insulin, resulting in reduced glucose uptake and increased hepatic glucose production, contributing to elevated blood glucose levels. Mechanisms driving insulin resistance include excess adiposity, chronic inflammation, and accumulation of ectopic fat. Impaired insulin receptor signaling and activation of stress kinases also play a role in insulin resistance development. Furthermore, insulin resistance also impairs the efficient clearance of triglyceride-rich lipoproteins by inhibiting lipoprotein lipase activity and reducing the expression of hepatic receptors involved in lipoprotein clearance. Another important factor contributing to dyslipidemia in metabolic syndrome is the elevated levels of pro-inflammatory cytokines, such as tumor necrosis factor alpha and interleukin 6. These cytokines disrupt lipid metabolism by inhibiting insulin signaling pathways and promoting lipolysis in adipose tissue, leading to increased release of free fatty acids. In summary, dyslipidemia in metabolic syndrome is a complex process involving dysregulation of lipid metabolism and transport. Adipose tissue dysfunction, insulin resistance, impaired lipoprotein clearance, and inflammation all play pivotal roles in the development and progression of dyslipidemia in metabolic syndrome. Thus, adipose tissue dysfunction in metabolic syndrome involves both inflammation and alterations in adipokin secretion, contributing to insulin resistance, inflammation, and disrupted energy balance. Understanding these mechanisms is vital for early detection and targeted treatment of metabolic syndrome. In metabolic syndrome, chronic low-grade inflammation plays a significant role in insulin resistance and vascular dysfunction. Inflammatory pathways like NF-kappa B and the inflammasome are involved, leading to the release of pro-inflammatory cytokines that worsen insulin resistance and impair glucose uptake. In summary, oxidative stress and mitochondrial dysfunction are key contributors to metabolic syndrome. Excessive production of reactive oxygen species, ROS, in conditions of nutrient excess leads to harmful effects on lipids, proteins, and DNA, contributing to insulin resistance and vascular dysfunction. This oxidative stress is further worsened by impaired mitochondrial function, resulting in increased ROS production, decreased ATP production, and altered fatty acid oxidation. Therefore, understanding the role of gut microbiota in metabolic syndrome development is crucial for developing targeted therapeutic approaches that can restore gut microbiota composition and improve metabolic health. In summary, endothelial dysfunction is a key factor in the vascular complications of metabolic syndrome. It is characterized by impaired vasodilation, a pro-inflammatory state, and is influenced by factors like oxidative stress, inflammation, and insulin resistance. In summary, adipokines are molecules produced by adipose tissue that play a crucial role in regulating energy balance and insulin sensitivity. In metabolic syndrome, altered adipokin levels contribute to insulin resistance and chronic inflammation. Specifically, reduced levels of adiponectin and leptin resistance play a significant role in the development and progression of metabolic syndrome. Non-alcoholic fatty liver disease, NAFLD, is a condition where fat accumulates in the liver due to factors like insulin resistance and dyslipidemia. It can range from simple fat accumulation to more severe inflammation and scarring of the liver. Factors like inflammation, oxidative stress, and gut bacteria also play a role in disease progression. The renin-angiotensin-aldosterone system, RAAS, plays a crucial role in the regulation of blood pressure and fluid balance. In individuals with metabolic syndrome, dysregulation of the ROS contributes to the development of hypertension, a common feature of this syndrome. Insulin resistance directly affects the ROS by enhancing the activity of the angiotensin-converting enzyme, ACE, and increasing the production of angiotensin II, a potent vasoconstrictor. Elevated levels of angiotensin II promote vasoconstriction, sodium retention, and increased sympathetic activity, leading to increased blood pressure. Furthermore, adipose tissue dysfunction in metabolic syndrome results in dysregulated production of adipokines, such as adiponectin and resistin, which can directly influence the ROS. Adiponectin exhibits antihypertensive properties by inhibiting ROS activation, while resistin promotes ROS activity. Genetic factors play a significant role in the development of metabolic syndrome. Various genetic polymorphisms have been identified that predispose individuals to metabolic abnormalities, including insulin resistance, dyslipidemia, and hypertension. Polymorphisms in genes involved in lipid metabolism, such as the peroxisome proliferator activated receptor gamma, PARG, gene and the apolipoprotein C3, APOC3, gene, have been associated with dyslipidemia and metabolic syndrome. These genetic variants affect lipid metabolism pathways, leading to altered lipid profiles. Furthermore, polymorphisms in genes related to glucose metabolism, such as the insulin receptor substrate, IRS, gene and the melanocortin 4 receptor, MC4R, gene, contribute to insulin resistance and the development of metabolic syndrome. These genetic variants impair insulin signaling pathways and disrupt energy balance, promoting the development of metabolic abnormalities. To summarize, pharmacological interventions targeting the components of metabolic syndrome include medications like metformin and TZDs for insulin resistance, statins for dyslipidemia, and ACE inhibitors, ARBs, and calcium channel blockers for hypertension. Lifestyle modifications are also crucial in managing metabolic syndrome. Metabolic syndrome, a group of metabolic abnormalities, heightens the risk of cardiovascular disease and type 2 diabetes. Identifying its multifactorial causes is vital for effective treatment, combining lifestyle modifications and medication to decrease cardiovascular complications.